Welcome and thank you for joining us for today's webcast, Advanced Thermal Management Technologies in Medical Devices, sponsored by Advanced Cooling Technologies and Tech Briefs Media Group. I'm Billy Hurley, Associate Editor with Tech Briefs Media Group, and I'll be your moderator today. Our webcast will last approximately 30 minutes, and there will be a question and answer period at the end of the presentation. If you have a question, you may submit it at any time during the presentation by entering it in the box at the bottom of your screen. Our presenter will answer as many questions as possible at the conclusion of the presentation. Those questions not addressed during the live event will be answered after the webcast. Twice during the presentation, we'll also present you with a poll question, and we invite you to answer those as they appear. In order to view the presentation properly, please disable any pop-up blockers you may have on your browser. At this time, I'd like to introduce our main speaker. Pete Ritt is Vice President of Technical Services at ACT. ACT's technical services business provides thermal consulting, design, and analysis to a variety of industries, including medical devices. Mr. Ritt is a former RCA Thompson executive, where he most recently was Manager of Strategic Programs and Business Manager for the Lancaster R&D Center. In that role, he was responsible for developing technologies, processes, and products for scale-up and commercialization, which is common to some of his responsibilities at ACT. He has been granted over 20 patents and holds degrees in chemical engineering from the University of Notre Dame and an MBA from Shippensburg University. So at this time, I'd like to hand the program over to our first speaker, Pete Ritt.
Thank you, Billy. I'm Pete Ritt, and along with Rich Bonner, we are delighted to be with you. For today's presentation, we'd like to give you an overview of thermal management in medical devices and then introduce some new technologies that are now available to the medical device design engineer facing thermal challenges. Specifically, we'll review and discuss passive thermal management solutions, heat pipes, vapor chambers, and phase change materials, and then explore where these technologies are and can be employed. Medical devices, like many electronic devices, are experiencing trends of increasing power with decreasing packaging size. They are smaller, more functional, and more powerful. And this requires greater emphasis on thermal management solutions. But medical devices have additional requirements. They also have the human element to consider. For example, devices that directly contact the skin must be kept below FDA-mandated limits of 41 degrees C. Also, material selection is limited due to contamination concerns. Copper, for example, can't be used in some devices for this reason. Noise from pumps and fans can be irritating and problematic for both the patient and the operator. With these smaller, more powerful devices, many of the traditional thermal management solutions, like metal heat sinks and cooling fans, need to be updated or augmented with other technologies, such as the one we will be discussing today. We see a growing need for these passive thermal solutions in medical devices and thought it would be beneficial to explore them in a little more depth. Here are some examples of thermal management issues in medical devices that we've come across. Undoubtedly, there are many others. Some ultrasound machines have 6 feet of water cooling lines to keep the handle cool enough to touch. The 6 foot of cabling can be a safety factor for both the patient and the operator in terms of tripping and leaking, not to mention skin irritation that may occur if the pumping malfunctions. MRI machines must hold tight temperature control to maintain calibration. There are lots of options for thermal management, but when adding the extra requirement of quiet operation, solutions other than pumps and fans may need to be implemented. There are safety regulations which limit the maximum temperature which surgical devices can be safely used. We previously mentioned temperature limits for skin contact. Listed here are temperatures for brain surgery and laparoscopy. Maintaining devices below these temperatures can provide for faster treatments, higher throughput, and less downtime. Finally, PCRs, polymerase chain reactors, thermocyclers used in DNA replication, require very good temperature uniformity across the processing area. I listed 0.2 degrees C as the typical uniformity spec, but some are even tighter. These devices also need fast response times, changing temperatures at 2 to 5 degrees per second while maintaining that uniformity. As I mentioned, these are just some applications of thermal management in medical devices. Of course, there are more, and the principles and the technologies that we will be discussing today are applicable to all of these. When we are discussing these advanced thermal technologies, we are referring to two groups. The first is passive technologies. Now we're on the right one. First is passive technologies, heat pipes and vapor chambers. They require no input power to operate, they provide years of reliable operation, and they operate with virtually no noise. Closely aligned with heat pipes and vapor chambers are phase change materials. PCMs can be used to handle short-term peak loading of thermal input. They can handle peak thermal demand. PCMs also allow system designers to size their thermal solutions for the average thermal load, not the peak load. PCMs save space, weight, and cost. And now it's time for our first polling question.
Thanks, Pete. At this time, we'll present you, the audience, with our first poll question. Shortly, the poll question will appear, and we invite you to select one of the choices by clicking the appropriate button on your screen. So our first question is, who does your company use to resolve critical thermal management issues? Your choices are A, in-house resources, B, external experts, C, a combination of both in-house and external resources, or D, not sure. So you can select A, B, C, or D at this time. The question is, who does your company use to resolve critical thermal management issues? In-house resources, external experts, a combination of both in-house and external resources, or not sure? Back to you, Pete.
Thanks, Billy. For today's webinar, we're going to look at these three technologies, heat pipes, vapor chambers, phase change materials. We'll also be looking at a subset of heat pipes, high K or high conductivity plates. First, we'll look at heat pipes. Heat pipes are sealed vacuum devices. They are housed in a metal tube. Inside the tube is a wick structure and a small amount of a working fluid. Most applications are copper tube, copper mesh wick structure, and water, but there are several other envelope materials, wick structures, and working fluid combinations. Heat pipes are passive, two-phase heat transfer devices that operate in a closed system. To work, a heat pipe must be connected to a hot end, or evaporator, and a cold end, or condenser, and as can be seen in the schematic on the left. The delta T is the driving force. The heat from the evaporator causes the working fluid to vaporize. The vapor then flows to the cooler end, where it condenses to a liquid. The condensed liquid then returns to the evaporator by capillary force of the wick structure or by gravity. In the schematic on the right, you can see a cutaway showing the heat pipe structure, including the center vapor path and the liquid path along the wick structure. So now that we know a little bit about heat pipe operation, let's see how this can be put to use. First of all, with different combinations of envelope material, wick structures, and working fluids, heat pipes can be used over a wide temperature range, from cryogenic to liquid metal, from about -150 to around 1,000 degrees C. Because these are sealed vacuum devices, some working fluids can operate beyond their nominal boiling point. Water, for example, can be an effective working fluid from 20 to 250 degrees C. By controlling the amount of working fluid and then selecting the appropriate wick structure, heat pipes can restart after freezing. They are freeze-thaw tolerant. Also, with the right wick structure, heat pipes can operate against gravity. Typically, heat pipes can transfer heat around 8 to 10 inches against gravity, although gravity-aided operation is generally preferred. In terms of advantages, since boiling and condensing are occurring at the same temperature, heat pipes can have effective conductivities of 10,000 up to 200,000 watts per meter Kelvin. We can contrast this with copper, an often used conductor, which has a conductivity of around 400. Other advantages include continuous passive operation, excellent isothermality characteristics, and quiet operation. In terms of heat flux capabilities, heat pipes can operate with heat fluxes up to 50 to 75 watts per centimeter squared, and with custom wicks up to 500 watts per centimeter squared. One of the key benefits of heat pipes is heat transport. Heat pipes can be used to transport heat to external sinks. They are capable of transferring heat over long distances with minimal delta T. We mentioned typical heat pipes can transfer heat 8 to 10 inches. Gravity-aided and other specialized heat pipes can transfer over longer distances. The typical delta T is about 2 to 5 degrees C over the length of the pipe. Bending and flattening enables increased geometric flexibility to design. You can see in the picture on the lower right heat pipes which are bent in 3 dimensions to transport heat away from an electronic component to a cold rail. Finally, heat pipes can be used to move heat away from the inside of an enclosure to exterior air cooling without subjecting the components to the outside environment. So when should one consider using heat pipes? Essentially any time high conduction gradients are a major portion of the thermal resistance. Heat pipes can be used to both transfer heat and isothermalize components. In terms of benefits, heat pipes can be used to reduce the thermal management system size by providing more efficient heat transfer. They can also reduce system weight. Heat pipes are evacuated metal tubes, which are lighter than similar-sized metal rods. They can reduce required power. Heat pipes themselves require no power to operate, and they can decrease system hotspots. In terms of flexibility, heat pipes can be formed to fit countless geometries. The typical bending radius for a heat pipe is 3 times the outer diameter, and they can be flattened to 2/3 the outside diameter. An operating heat pipe bent around a penny can be seen in the lower right. One specific application of heat pipes is high K plates. High K plates are aluminum conduction plates with heat pipes embedded in them. Aluminum silicon carbide can be used instead of aluminum for direct die attachment applications. A sample AlSiC high K plate is pictured on the upper right. Typical thermal conductivity for aluminum high K plates is 500 to 1200 watt per meter K, contrasted to aluminum, which has a thermal conductivity of around 200. High K plates can be used to reduce hotspot temperatures. They can serve as enhanced conduction-cooled cold plates. They can be used for liquid or air-cooled chassis. They can be used to improve fin efficiency and lower fin weight. Pictured on the lower right is an IGBT application where all of the high-powered electrical components were located on one side of the heat sink. Heat pipes were used to spread heat and get improved fin efficiency. Plate thickness is typically 4 millimeters, and the structural strength and weight of a high K plate is approximately the same as aluminum. And for reduced weight applications, magnesium can be used in place of aluminum. Shown here is a thermal analysis of an aluminum plate containing several high-powered electrical components with and without embedded heat pipes. On the far left is a solid aluminum plate without any heat pipes. You can clearly see the 3 hot spots, 2 at the top and 1 at the bottom. Pictured in the middle is that same aluminum plate, but now with heat pipes embedded in them. You can clearly see that the maximum temperature has dropped about 20 degrees, and the temperature uniformity of the plate has improved greatly. Pictured on the right is that plate with the heat pipes. Heat pipes can be seen as the silver structure in the plate. Next, we'll talk about vapor chambers. Vapor chambers work similarly to heat pipes, but operate in two dimensions. As can be seen in the schematic on the right, in vapor chamber operation, high heat flux causes the working fluid to vaporize. The vapor then spreads in two dimensions. There is wick material in the inside structure of the chamber where the vapor can condense and is returned to the high heat flux area. One of the benefits of vapor chamber is that the vapor heat transport yields nearly perfect isothermal heat spreading, as is illustrated on the low flux side in the right side of the schematic. So, in a sense, a vapor chamber is a heat flux transformer. Vapor chambers are often used in conjunction with heat sinks, taking advantage of their nearly isothermal output and making the heat sink more efficient. Typical components of a vapor chamber heat sink assembly are seen in the lower left. They consist of a vapor chamber wick structure in the middle, a copper envelope seen below, and a heat sink seen at the top. Also pictured is a multiple evaporator, low CTE, coefficient of thermal expansion, high heat flux vapor chamber prepped for direct die attachment of 4 chips. As can be seen, vapor chambers can accommodate multiple evaporators. Vapor chamber wick structures. ACT has developed a unique circulatory system wick structure to address the conflicting needs of high critical heat flux and low evaporator resistance. CHF, critical heat flux, is a thermal limit where the vapor covers the entire surface, causing it to heat up rapidly. In the novel system being described here, a thick feed wick delivers liquid to a thin evaporator wick. The vapor and liquid flow paths are segregated, but they are co-located. You can see this in the pictures below, where the walls or pillars are the thick wick material and the surrounding area is thin wick. With this system, CHF of greater than 500 watts per centimeter squared with very low evaporator resistances have been achieved. At these heat fluxes, vapor chambers can also be used to dissipate heat from some high-powered laser devices. So when should one consider using a vapor chamber? As a heat source, when the heat source size to heat sink size ratio is relatively large, 1 to 10 or greater, and also to enhance the performance of an existing air-cooled heat sink without increasing its size. And as a heat source, when the heat transport is in 2 dimensions, not in a straight line. And when a high K plate isn't good enough. Vapor chambers can handle higher heat fluxes, but they are a little more costly. Now it's time for our final polling question.
Thanks, Pete. Here is our second poll question, and it should appear shortly. The question is, are you facing any thermal management issues in the next A, 0 to 6 months, B, 6 to 24 months, or C, are you facing no immediate issues? You can select A, B, or C at this time. Again, the question is, are you facing any thermal management issues in the next 0 to 6 months, 6 to 24 months, or are you facing no immediate issues? Thanks, Pete. Back to you.
Thanks, Billy. Now we'll change topics and look at phase change materials. Phase change materials are substances with a high heat of fusion, which are capable of storing and releasing large amounts of energy when melting and solidifying at a certain temperature. As mentioned earlier, PCMs offer the design engineer the flexibility to design for the average peak thermal load instead of the max load. This can provide savings in packaging size, weight, and cost. PCMs are very effective for pulse-powered devices such as lasers, which have short bursts of high energy. Periods of off time are required to recharge the PCM to allow it to re-solidify. Common PCM materials include ice, paraffin wax, indium, salt hydrates, and some solders. PCMs can also extend product life by reducing the max temperature the device is subject to. Let's talk a little more about PCMs. Devices using phase change materials are very customizable to the heat load, temperatures, and frequency of the application. PCMs are generally not thermally conductive, so heat pipes and metallic foams are often utilized to conduct heat into the PCM. Common PCMs like paraffin waxes and the salt hydrates span the temperature range from -4 to 100 degrees C, and with solder, even higher temperatures can be achieved. Long-duration heat loads with long pulse durations typically require more PCM, while small, short-duration pulse transients may only require micrograms of PCM. In the following slides, the ability of PCMs to store and release small amounts of heat in a high-frequency communications chip is demonstrated. There it is. Here's an example of an application of a phase change material for a transmit-receive device. The system is a gallium nitride transistor with PCM operating at a high frequency. This system requires a small amount of PCM to store heat during a short pulse. Indium is used as the PCM. In the structure, a 1-micron gallium nitride layer is the heat source. Below that is an 8-micron indium PCM layer that sits on top of a 1-micron silicon substrate. Here's a simulation of the cycle of the device. It is a 10 microsecond cycle, 2 microseconds on, 8 microseconds off. Pictured here are 4 slices of that cycle. On each slice, the left-hand side is the temperature at the gallium nitride layer. On the right-hand side is the solid-liquid mixture of the PCM. As can be seen in the upper left, at time t equals 0, both gallium nitride layer and the PCM are at the same temperature. At time t equals 0.8 seconds, the 2 hot spots in the gallium nitride layer are increasing in temperature, causing the PCM in close proximity to begin melting. At time 2.0 microseconds, the end of the on cycle, the 2 hot spots are at maximum temperature, and there is a substantial amount of PCM melting. At time 4.52 microseconds, the gallium nitride layer is off and is no longer heating. The PCM is now acting as the heat source, dissipating the heat it absorbed during the on cycle. By completion of the 10 microsecond cycle, all of the PCM has re-solidified and is ready for the next cycle. Here's a graph of the multiple cycles. You can see the blue line peak temperature of the gallium nitride layer without PCM is about 172 degrees C. As seen with the beige-orange line with PCM, the gallium nitride peak temperature is lowered to around 140 degrees C, a significant reduction. You can also see that the substrate layer is only slowly increasing temperature and is reaching steady state by around 60 degrees C. Melt front, the point of the PCM layer that is changing from solid to liquid and back again, is also stabilizing around 60 degrees C. Imagine what kind of benefit this could provide to some pulse devices that are temperature sensitive due to either contact temperature or wavelength. Benefits include smaller packages, less downtime, greater throughput, and overall safer operation. Let's look at some selected applications for these passive technologies in medical devices. Heat pipes can be used in forceps for electrosurgery applications to quickly dissipate heat from the tip. This enables the surgeon to move quicker and safer during the procedure, reducing the risk of burning unintended tissue. Titanium heat pipes are generally used here. Heat pipes transport cold as well as heat and can be used for cryosurgery to precisely transport cold from an external cooling source to the surgery point. Vapor chambers can be used in PCRs in conjunction with thermoelectric devices to provide an isothermal processing platform to meet the challenging temperature uniformity requirements we discussed earlier. In this application, the thermoelectrics serve as the heating-cooling source. A typical PCR machine is pictured on the lower right. Vapor chambers can also be used to cool some high-powered laser devices. Phase change materials. PCMs are used in pulse-powered devices, as we have seen. They are also used to maintain stringent controls for temperature-sensitive items such as blood and tissue to ensure good temperature stability during shipment. So today we have presented 3 passive technologies with direct applications for improved thermal management in medical devices: heat pipes, vapor chambers, phase change materials. All 3 offer reliable, effective, quiet thermal management, but each has unique benefits. Heat pipes provide heat transport and heat spreading. Vapor chambers provide high heat flux spreading and nearly isothermal heat spreading. Phase change materials provide temporal thermal management for pulse devices. All will have increasing application in medical devices with increasing power and decreasing packaging design trends that we are experiencing. Thank you very much for your attention. Back to you, Billy.
Thanks, Pete. And I want to introduce another speaker who will help answer questions in the Q&A. Now on the line we have Rich Bonner, Manager of Custom Products. Bonner has been with Advanced Cooling Technologies for over 6 years. He has served as Principal Investigator on multiple government and industrial R&D programs involving advanced thermal management. The thermal topics have included two-phase heat transfer, nanoscale coatings, thermal storage, junction level cooling, and jet impingement. He also has served as a technical lead on many technical service programs, including aerospace, defense, medical, and commercial electronics cooling programs. He is currently a chemical engineering doctoral candidate at Lehigh University, where he also holds a master's and bachelor's degree. Hi, Rich. Thanks for being with us.
Hi, Billy.
Rich, here's our first question. We have time for a few. What is the typical thickness of vapor chambers?
Most of the vapor chambers we manufacture are in the 3 to 4 millimeter thickness range. However, it's quite easy for us to go thicker than that, but usually customers push us for the thinner performance. In some custom applications, we have gone down to 2 millimeters, and going smaller than that tends to be difficult, and also you tend to do loss of performance. So to answer the question, I would say 3 to 4 millimeters is quite typical.
Here's another question from an attendee. Would you comment on using heat pipes in a high shock environment where a CPU is shock isolated via shock mounts and the heat sink is in a fixed position?
Sure. Well, I think the key to this question is, do heat pipes function in a high shock environment? And what I would say is, in a high shock, temporarily the heat pipe may stop circulating fluid. However, you have to keep in mind the heat pipe does store some heat. So if it stops circulating for a second or two, your chip isn't going to run away. As soon as that shock event is over, the heat pipe quickly recovers and continues circulating heat. So in most shock applications, heat pipes are quite effective.
How does orientation affect heat pipe and vapor chamber performance?
This is a quite common question. Most people are aware that when operating a heat pipe gravity-aided, they can often do more power than operating against gravity. However, provided that your heat pipe is operating within its limits, the thermal resistance of the heat pipe is the same whether operating with or without gravity. However, the heat pipe or vapor chamber can circulate more power if necessary in a gravity-aided environment.
We have time for one or two more questions here. Are Wick structure materials different for heat pipes and vapor chambers?
Sure. We do utilize a number of different materials when designing wicks. I won't go into the details here, but as you can imagine, when designing a heat pipe wick structure, our design engineers have to consider how much power can it carry, trying to maximize the heat flux capability, and also trying to minimize thermal resistance. So we use a number of materials and different fabrication procedures when trying to optimize our heat pipe wick structures.
We have time for one more question, and if we didn't get a chance to answer your question, our sponsors will do their best to address it after the webcast. Here's our last question. What are the melting point temperatures for the more common PCMs?
Sure. The most common PCM materials are based on paraffin wax and also salt hydrates. And for those applications, usually around room temperature is most common. However, there are PCMs available that go between -4 degrees C and up to 100 degrees C using those types of materials. For higher temperature applications, you can go to metallic, basically solder-type materials that can melt at much higher temperatures.
Okay, thanks, Pete. Thanks, Rich. That'll conclude today's webcast. I want to thank everyone for joining us. Again, if we didn't get a chance to answer your question, our sponsors will do their best to address them after the webcast. And just a reminder, this webcast will be available on demand at www.techbriefs.com for the next 12 months. Have a great day. Thanks, Pete. Thanks, Rich.
Thanks, Billy.
Thank you.